We're really excited to have Simon Du speaking to us today. So Simon is an assistant professor at the Paul G. Allen School of Computer Science and Engineering at University of Washington. Previously, he was a postdoc at the Institute for Advanced Study in Princeton, and he did his PhD at CMU. His research interests are broadly in machine learning, and I'm really excited to hear him talk about the recent paper today on Is RL More Difficult than Bandits? Over to you.
All right, thanks for the introduction. So today I'll talk about our latest work on the tabular reinforcement learning. And the central problem we want to study is whether reinforcement learning is more difficult than bandits. All right, so on to thank for my collaborators, Zihan Zhang, who is a fourth-year PhD in Tsinghua University, and Xiangyang is also from Tsinghua University. So since this is RL theory talk, I'll just jump into the setting. So I'll review this tabular reinforcement learning. So in this talk, I'll mostly focus on episodic finite-Horizon Markov decision process. So basically, we are controlling an agent which is interacting with an environment. So at each time step, the agent is at some state, say ST, and the agent chooses some action, AT. The environment will move the agent to the next state according to some transition function, which depends on the state and the action, and it's a stochastic. Also, the environment will give this agent some reward, okay, according to some reward function, R, also depends on the state and the action. And for each episode, the agent will interact with the environment for H times. So we often call H to be the planning horizon or the episode length. And in this talk, I'll just say we play this game for totally k episodes. Okay, so this is the basic setting. And usually, we call our goal is to find a policy. So policy here you can think of as a function that maps the state to an action. Okay, and the goal is to maximize the expected total rewards, or we can also call it the value function. So the value function is defined as which is given a policy pi and starting state s. And the value function is defined as a expected total reward starting from S, and then you take the policy pi. And since this is a learning problem, we need to measure the sample complexity. So here we'll use the notion of regret to measure the sample complexity. So we'll compare the value function of the policies we execute during this game, which are this pi 1 to pi k, bk, and compared with the value function of the optimal policy, which is this v star function. Okay, and we calculate the difference between our executed policy and the optimal one. So this is the regret. Okay. Oh, by the way, if you have any question, please just interrupt or post it on the chat box. Okay. All right. So this is the basic setting about reinforcement learning. So I will also mention another simpler problem, which is the stochastic contextual bandits problem. So you can think of stochastic bandits as a special case with h equals to 1. Okay, so planning horizon is 1. So in this case, only the reward matters, okay, because there's no more transition here. At each episode, you sample some context from some initial distribution, and the agent choose some action and get some reward, and the goal is just to maximize this reward, okay? And again, we use this regret to measure the sample complexity. So there are two major differences between reinforcement learning and contextual bandits. One, there's no transition in the contextual bandits, okay? And here, also, since there's no, it's an h equals 1, so basically there's no planning horizon here, You don't need to consider the next state or so, which in RL is very important because you need to maximize the reward in the long run instead of just the immediate reward. And the central problem on study today is that is reinforcement learning really more difficult than Bandits due to these two major differences. Okay, so here we measure difficulty in terms of the regret. Okay. So today I'll especially focus on the tabular reinforcement learning, or tabular MDP, which is mostly the most basic setting we can think of. So here we have a finite number of states and finite number of actions, and the bounds, or like regret bounds, will depend on the number of states, number of actions, and possibly depend on the planning horizon H. And here for normalization, I'll assume the total the reward is non-negative, and total reward, the sum of all the rewards through all the episode, is upper bounded by 1. So let me spend one slide about this reward scaling because it's kind of important to state it more formally and compare it with existing works. So in contextual bandits, often we assume the reward is bounded by 1. So usually regret will scale with the total reward. So regret will scale by 1. Okay. And in most paper in reinforcement learning, people assume each reward at each time step is bounded by 1. Okay. And so for all time step, the reward is bounded by 1. So, however, if we want to compare reinforcement learning with bandits to have a fair comparison to study whether the unknown transition and the long planning horizon make reinforcement more difficult, this is not a fair assumption. The reason is that if you have a reward, each reward bounded by 1, then the total reward now is bounded by H, and the regret will scale up by an H factor. So in this setting, if your total reward is H, even in the bandit setting, you will scale up your regret by an H factor. Okay. So in order to have a more fair comparison to study the difficulty due to transition, unknown transition, and planning horizon, we need to scale down the reward by an H factor. Okay. So now here comes this assumption that each reward is bounded by 1 over H. So now the total reward is bounded by 1, and the regret will scale with 1. Okay. However, for this assumption, you can see there's a problem that if the H is very big, then the per step rewards are very tiny. Okay, which cannot model many real world problems. So here we can work with a more general assumption. That is, we assume the reward is non-negative, and the sum of the reward is bounded by 1. Okay. The benefit of this generality is that we can model very sparse and spiky reward. Like in one place, you can have a reward as high as order 1 instead of 1 over H. And you can see more discussion in, for example, Sham's thesis or Zhang, Nanjiang, and Aleka Gao's paper in 2018. Okay. All right, so now let me review some existing results. So I'll state these results in terms of the paper, the algorithm, the regret bounds. So regret bounds in terms of either the rescaled version of the uniform bounded reward or the total bounded reward. Okay, so here this is what we call uniformly bounded reward, and this is what we call the bounded total reward. Okay. So the lower bound in this setting is actually just the bandit's lower bound. So this is a classical result, and with some slight modification, you can modify the bound to have a bound for the uniformly bounded reward as well. But the structure of that lower bound is still like a bandit structure. Okay, but the key thing here, you can see the regret does not depend on the planning horizon. Okay. Now let's go to the upper bound. So to my knowledge, the first bound is by Kearns and Singh in 1998. It's called E cube, and they gave like the first polynomial bound in terms of the number of states, action, and the planning horizon, and some sublinear like regret term. And they were, at least in their original papers, working this uniform bounded reward assumption. Okay, so this is the first work. So later in 2010, Joshua and Altner and Auer to give this UCRL2 algorithm. So this bound significantly improved the original bound because it get a square root of k type of bound, but it still have a dependency on s squared, number of action, and this h squared term. Okay. And later in 2017, by Azar, Osman, and Bonus to give an improved bond, UCB VI with Bernstein bond. So these bonds have these terms. The first term is square root SA plus h times k plus second term, which is s squared AH. So this result, I think, is significant because you can see if SA is much larger than h and k is very large, then the square root of SAK dominates this bond. And this bond actually matches with the Bandits lower bound. Okay. At least this is for very large k and large SA regime. And then later in 2018, there's a paper by Jin, Alan Zhu, Sebastian Bubeck, and Mike Jordan to give a model-free algorithm. So you can see here, previous work mostly have time scale with s squared, but here the computation time scale with s, because they don't need to explicitly build the transition matrix in their algorithm. But their bond is worse than the previous best bond. It's square root of SAHK plus some additional poly terms.
Simon, I forgot. Let me ask quickly. Previous slide it was probably on. Are you considering the homogeneous or inhomogeneous setting in terms of the
sorry. Yeah, we consider the homogeneous setting, like the stationary or stationary setting.
And these guys consider the inhomogeneous setting. And I guess maybe later on we'll have a discussion about the differences between what you can expect to see in the homogeneous and inhomogeneous setting. So the number of parameters that they have is actually scaling with h, right?
Yes, in the inhomogeneous setting, we'll scale with h.
And so, right. So
yeah,
there that is applicable to the inhomogeneous case.
Right. I think by adapting their bond, you can. It's not hard to get like this kind of bond in the homogeneous case. That's why I put it here.
Oh, actually, okay, maybe save this to the controversial part.
Okay, yeah, sure. Yeah. So to clarify, we're working in the homogeneous case, like the number of total parameters does not scale with h. And later, there's a paper by Dan, Lee, Wei, and Brunskill. They can get rid of this square root of hk term in this others paper. Okay, so now we are in 2018. So in 2018, there's another very interesting open question asked by Zhang and Gao in code. They ask that under the bounded total reward assumption, okay, the total reward is bounded by 1, they conjecture that there's an h to the alpha, or like basically a polynomial of h lower bound, required lower bound. The reason is that all the state-of-the-art method in 2008, before like up to 2018 has some polynomial dependency on h, although the lower bound of contextual bandits does not depend on h. And conceptually, the common belief is that reinforced learning is really more difficult than bandits because of this long planning horizon. So you should expect there's some lower bound appear in, like h lower bound appear in like h dependency in the lower bound. Okay, so this is their conjecture. And later, after this open problem, Andre and Emma in 2019, they gave a new algorithm. So this algorithm is also very significant because their algorithm can work with the total bounded reward setting. And their dominating term, like when k is very large, does not depend on h, and it matches the Bandits lower bound. However, they still have some additional terms that depend polynomially on h. Okay, so later there's a work by my collaborators, Zihan Zhang, Yuan Zhou, and Xiangyang in 2020. To give a model-free algorithm, which works in the stronger assumption, uniformly bounded reward assumption, but their first term matches the Bandits lower bound. And earlier this year, we have worked together with Ruosong Wang, Lin Yang, and Sham. So we want to attack the conjecture by Nan and Alec. So we give a new algorithm which runs in exponential time, but the significance here is that the bound does not depend on h anymore. Okay. So this refutes the conjecture by Nan Zhang and Alec Gao. Okay, so this is earlier this year, and now also I would like to say the dependency on S and A also much worse than previous work, and also the dependency on the K. Okay. Sorry, is there a question?
Yeah, actually, is it actually? Yeah. Asking whether unif R means that the rewards are in 0 to 1 over h.
Yeah, uniform it means, let me see, pull out the slides. Uniform means rewards 1 over h. And bounded to the rewards, the total reward bounded by 1.
Right.
Okay. All right. So, and today we'll give the new algorithm. It's the latest work in this line of work. So our algorithm called MVP, and our regrets is the tightest up to date. So it's square root of SAK plus some one additional term S squared A. Okay, and our algorithm's running time is S squared AH because we are using a model-based approach. So let me spend a little bit more time on the significance of results. So we can work with this totally bounded, more general assumption on the reward. And our bound is square root of SAK plus S squared A. So this is the first polynomial time algorithm with regret scales logarithmically with the planning horizon. So it only appears in this O tilde. So some polylog factor there. And this exponentially improves all existing polynomial time algorithm in terms of regret because they all have some term that polynomially depend on the h. And more importantly, I think our result gives more hope to say that reinforcement learning may not be harder than Bandits because we are really approaching the contextual Bandits lower bound, okay, up to this S squared A term. So our bound, is near optimal up to log factor in the regime as long as k is in the this order. And I think the next open problem is to get rid of S squared A term. And then we can basically claim, reinforcement learning is almost as easy as Bandits in terms of regret. Okay. There are more questions? So in the following, I'll talk more about the technical details about our work.
So I actually have some questions that go somewhere in between the bandit and the reinforcement learning words. So there's like a bunch of papers on combinatorial bandits, right? Which would include shortest path problems, which would be like learning in a deterministic MDP. And there, I think a lot of people actually looked at the scaling with all these parameters, which is the length of the longest path and the number of edges in the graph. And so can you comment on the relationship between that, or are you familiar with those results at all?
I'm not very familiar with combinatorial bandits, but I can say that in deterministic system, I think you can match the, even in the linear, for the deterministic system, I mean, the transition and the reward are deterministic. Even with linear function, with some function approximation scheme, you can match the bound of reinforcement learning can match the bound of the bandits. So it's not new that reinforcement learning is as easy as Bandits. So here we'll focus on the tabular setting.
Yeah. So what I mean is that, in this shortest path problem, I think, there the same question has been asked before, right? Like, can you eliminate these factors of
I'm
the
not very familiar
horizon
with
and the scaling factors?
I'm not very familiar with literature there, but yeah, maybe you can discuss later for
yeah.
that
So I guess I guess from there it is like sort of obvious already that, well, learning with a long horizon is like not necessarily a problem. So like the length of the horizon is not always going to show up in the bounds. But here, like, I guess in this reinforcement learning problem, it's far from obvious, because here you have to learn the transitions.
Yeah, just a very high level comment is that if you have a deterministic system, then you very quickly learn the transitions. So you may as well assume that you know the transitions. If you know ahead of the transitions in a deterministic system, it's a very different setting than if you're learning stochastic transitions. Basically, you hear the question being asked is whether the stochastic transitions are going to cost you much. But you are right, Yagu, that there is this connection, which is kind of interesting.
Yeah, right. I mean, it wasn't really like any criticism of this, or I wasn't like really pointing out that this was like a relevant omission. I'm just saying that, well, in a different context, this question has been asked and answered positively, that yes, you can get rid of these horizon factors. Yes, but we can talk more about that later. Yeah. Awesome, thank you.
Any more questions?
There are all kind of things going on the chat.
Actually,
no, don't look. Like I'm gonna translate or whatever. How many slides do you have?
I have like 12 more slides, but there are like technical details. I can answer some questions.
Yeah, okay. So there is this idea, like I was just trying to figure out whether we should like leave these questions later, but there's this idea that like if you have a deterministic system, then maybe the S squared A, like that kind of shows that the S squared A should be there, right? Like, because just to learn the deterministic transitions, and like you basically have to try things.
Yeah, I mean, as A definitely will show up there, but I don't think you need H, especially for a deterministic system. Pretty sure.
But like for the lower bound, like in terms of a lower bound, like I think that if we want to fix the Bandits lower bound, that is an obvious way to add the S squared A. At SA is definitely sure.
You mean you have an S squared A in the lower bound for this lower term?
Yeah, just take a deterministic system, and you need to learn where it goes in order to do well. How are you going to propose to do that without transitions?
I'm not sure.
Maybe it's SA, but not S squared A. But
because deterministic, you only have one.
So SA. But maybe that's actually the lower bound.
Yeah, the question is, I guess, can you replace that S squared A with the number of like non-trivial transitions or non-zero transitions?
I see.
For example.
That's possible, yeah.
Well, and also fix the lower bound, right? Ooh,
all right.
What did I do?
Maybe let me continue now. All right, so the algorithm is based on the value-based learning. So we're trying to estimate the Q function. So the definition of the Q function is the following. So the Q function depends on a policy pi and the current level small h, which is from 1 to big H, and depends on a state action pair. It represents the expected rewards, total rewards, starting from state S, and you take action A, and then you follow the policy pi. So people often use Q function because it's very convenient. If you know the optimal, the Q function of the optimal policy, so let's note as Q star, then you can derive the optimal policy from the optimal Q function. Basically, you can just act greedily by choosing the action that maximize the Q function. Okay. And a very important property about Q function is the Bellman equation. So this is the notation I'll use. So you can basically expand your Q function one step. So Q h pi SA equals to the reward of SA plus this basically expected value of the next level. So P here is an PSA here is an S-dimensional probabilistic vector, and V pi is again an S-dimensional vector. It represents the values of the next level. Okay. So their inner product basically represents the expected value of the next level if you use policy pi. Okay. So this is a basic definition of value-based learning or Q function. So our algorithm also use is an optimistic style algorithm, which many previous work used. So for this kind of style algorithm, basically try to calculate an estimation of the optimal Q function. It's denoted as Q hat for all the state action pair and the level H. And being optimistic, I mean that our estimation is always an upper bound of the optimal Q function. Okay. And suppose we have this kind of estimation, we can just our policy at the say episode K is just the greedy policy according to this estimated Q function. And in terms of regret, so because we know our Q function's estimation is an optimistic, our V function's estimation is also optimistic because we are just taking the max of the Q. And then basically we can rewrite upper bound regret in terms of our estimated V function, the difference between our estimated V function and the value of the policy we actually execute. Okay, because this V hat is always bigger than V star. Okay, so many algorithms follow this framework. But there are two main questions. Like first is how to estimate Q star. What is your estimator, and how do you ensure the optimism? And secondly, how do you actually bound the difference between your estimation and the value of your policy you actually execute? Okay. All right. So we'll use some model-based estimator for the Q function. Sorry, there's a little bit heavy annotations here. So basically, before the case episode, small case episode, you have this data, which is state action and next state tuples from k prime from 1 to k minus 1 and small h from 1 to big H. And here we'll assume the reward is known because the estimation of the reward only incurs smaller order term. Okay, so for that, we'll just compute by counting the empirical transition. So we just count number of state action next state tuples in the data set, and we count the number of state action pairs in the data set, and we can compute this empirical transition matrix. Okay, for every state action and next state. And then we can use this to estimate the Q function and V function using Bellman equation. So the updates according to this rule. So we'll let the last value, like or VH plus 1 equals 0 for simplicity. And then we can iteratively define our estimator, for example, for level H and for state action pair. According to Bellman equation, that's the reward plus our empirical estimate of the transition and our estimation of the V function of the next level. And we also need to add some bonus function, which we call B or BH, on this action pair to ensure the optimism. Okay, our estimation is always an upper bound of the optimal Q function. And for the V function, we just take the max of the estimated Q function. Okay. I hope this is clear. If you have any clarity question, please ask.
Yeah. I had the query in the algorithm, and you have used a minimum of this Q function with a constant value. Why is that the case?
Sorry, the minimum of Q function?
The minimum of the Q value, and the constant. So I was referring to the algorithm.
Oh, the algorithm like this.
Yeah.
I mean, there's no constant. So basically, we compute some Q hat, and we need to ensure that it's bigger than Q star. And the question is, how do we compute this Q hat?
Okay. So it might be the difference between. Oh, I got that. Thanks. Yeah.
Okay. All right. So, are there any more questions?
Very good.
Okay, cool. So I want to mention there's a trade-off between optimism and the regret. Remember, we can bound regret in terms of the summation. And basically, you can bound the summation in terms of the sum of total bonus in your construction based on additional terms. Okay, but here you can see the summation of the bonus from small k to small k equals 1 to big K and h from 1 to big H. So basically, here's a trade-off between a bonus and regret, because if you have a larger bonus, you can definitely ensure the optimism. But according to this inequality, if you want to bound the regret, you have larger bonus, you have larger regret, at least in the analysis. So we want to find a tighter bonus because it will give us smaller regret. Okay. So the first attempt to design the bonus is by Hoeffding Bonus. Remember, our random variable is this stuff. So it's a p hat inner product with the v hat of the h+1 level. And we want to bound the difference between this inner product and that of the replace p by the true transition and replace v hat by the true or the optimal v function. Okay, this is our random variable. We want to have a confidence bound so that we can upper bound this term plus the bonus. It's an upper bound of the true inner product between the transition and the value function. So we can just expand to write it as p hat minus p multiplied by v star plus p hat multiplied by the difference between v hat and v star. And the second term is always a non-negative term because we have optimism at level h+1. So this is non-negative, and you remember p hat is always non-negative. So we can lower bound it by this term. Okay. So you can see here, this term is a zero mean because we use an unbiased estimate of the transition matrix, and it's bounded because remember v star is bounded by 1, and this is a probabilistic vector, so this is a bounded random variable. And so then we can just use Hoeffding inequality, so we can set the bonus to be proportional to some square root of 1 or number of visitation of the state action pair. Okay. Basically, we can bound the sum of the bonus, which usually is the dominating term for the regret, by the pigeonhole principle, and you will get this kind of regret bound. It's like square root of SAHK. Because the summation in total, you have HK terms. So in the regret or in the bound, you will have an HK term as well. So this H is now tight. Okay, so how can we do better? So instead of using Hoeffding, we can use Bernstein bound. Okay, so remember this random variable is bounded again and zero mean. So instead of using Hoeffding, we can use more precisely an empirical Bernstein inequality to construct the bonus. So we can set the bonus proportional to the summation of two terms. The first term is the variance. So here, let's consider we know the true V star. And then, so you can set the bonus. The first term of the bonus is square root of the variance of this random variable. Okay, this is p hat and V star divided by the number of visitation of state action pair plus an additional 1/n SA term. Okay, so this is a fast rate term. So even if you sum over all of them, it only will contribute to a log term. And the variance here, yes.
There is an inner product missing between the p hat and the V
Oh
star.
yeah, sorry. Yeah, there's an inner product between p hat and V star.
Yeah,
right. So the variance here is the so it's just like normal variance. We view P as a probability distribution. P hat is distribution, and we have random variable V star. So the variance of this V star is just the inner product between P hat and V star square. So here square is an entry-wise square. Remember, this is an S-dimensional vector. Minus the inner product between these two. This is basically expectation, and then you take the square. Okay, so that's why we call this variance. So this term will be the dominating term. So we can bound this term again by some. So first we can use Bandits inequality to bound it by this term, and then we can use another So in the first inequality, we can replace the p hat by p by Bandits inequality. And then we can further use the law of total variance, which I'll talk more later, which is very tricky stuff, to say that the summation of these terms bounded by square root of SAK. So importantly, here there's no H term here. But even if you add in your summation, you have from H from 1 to big H. So in this part, we'll use the assumption that the total reward is bounded by 1. However, before that, there's an important missing part, is that in order to build this confidence bound, you need to know the true V star, okay, of the level H plus 1. But we don't know the true V star. So how can we do it? So until this part, this is unknown before our work. And previous work, mostly to deal with this problem, to ensure optimism, you can use the plug-in estimate. You can replace V star by your estimated V hat. But this is not although V hat is bigger than V star, that does not mean that your variance is bigger than the variance of V star, okay? So in order to ensure optimism, you need to add usually many additional terms in terms of the difference between your estimated V and the true V star. For example, natural idea to estimate, you first estimate the difference between these two under certain norms. However, if you really use this report, the estimation error of estimating the norm of the difference already will incur an poly H factor, although usually in the second term of the regret. So most previous work using this UCB and Bernstein type bound algorithm will have this additional H factors. So these H factors all came from your kind of estimation of the difference between your V hat and V star. Okay, so this is a previous approach. So our key novelty in our paper is a new approach to construct the bonus, what we call the monotonic value propagation, like MVP. So the idea is the following. So instead of we view this bonus as a function of two inputs. The first input is your probability vector or your estimated transition matrix. The second input is a V function of the next level. Okay, so wanted to ensure two properties. The first one is optimism. That is, suppose we use the true V star in our function. Okay, then we should get this ideal bound, or at least in the upper bound of the ideal bonus. Okay, which we talked about before. This kind of square root of the variance of V star divided by NSA plus some C2 times 1 over NSA. Okay. The second property is new. It's called the monotonicity property. Okay, it's the following. So we want to ensure this bonus to satisfy that for all V hat, so this V hat is more than 1 and bigger than V star. So it's an optimistic estimation of V star. And P hat is an probabilistic vector. Then our bonus is still ensuring optimism of the in terms of the bonus of the true value function. Okay. So if we use a bigger V hat, our function is as bigger as well. So if we have these two properties, then we directly have this desired optimism, because we can first replace V hat by V star, and this V star, but first property is bigger than the bonus of this V star is bigger than the ideal bonus we have. Okay, so we want to construct a bonus that satisfies these two properties, and the construction is very, very easy. You just need to tune the constants in your bonus. For example, we can set it to be these two constants, and this function satisfies these two properties. Okay, this is very, very easy. As long as you do some simple calculations, you can see this is the case. And I want to say that this is simplest Bernstein bound, because all the previous work all have many additional terms, but we only have these two terms in our bonus bound. And these two terms are necessary if you want to use Bernstein bound. Okay, so this is our first innovation. It's only a one-page proof to ensure the optimism and the monotonicity. Okay, and now I want to say the second non-trivial part is about bounding the sum of the variance to the square root of SAK. Okay. I'm sorry about the heavy math, but the idea is the following. So first, we can use pigeonhole principle to separate the square root of SA and the summation of the variance. So remember, this summation is from small k from 1 to big K and small h from 1 to big H, and sum of their variance. So naively, you can bound it by HK, but it's not tight. We want to have a very tight bound. So our idea is the following. So we can use Friedmann inequality to relate this term to its higher moments. Okay. So it's bounded by, again, the summation of the variance, but here the variance is on the V star square. So basically here you have a fourth moment in this expression. Okay. So replace V, the variance of V star, by the variance of V star square. And then according to Friedmann inequality, we'll have some additional terms in terms of K. So here, after calculation, you have, here's a Ka squared. And then the whole thing to the power of 1/4. Okay. So this is one step of expansion. And actually, some previous work already tried this approach. And if you use this approach, like one-step expansion, you can get dominating term to be square root of SK, but you still have some additional term that involve polynomial dependency on H. So what we do is we further expand using the same idea, using Friedmann inequality many times, say m times, small m times. So after this, we'll have this inequality that is smaller than square root of SA times this stuff. This stuff is a summation of the variance of the V star to the power of 2 to the m. okay, plus some additional term, which is k to the 2 to the m minus 1. And the whole thing to the power of 2 to the negative m. So basically, you just replace the Friedman inequality m times, you will arrive at this kind of inequality. Okay. So now we know that the first term is actually very small, because that we know the variance is for any m, because value is smaller than 1. The summation of them is always smaller than hk. Okay. So you can replace this by hk. And then you just work backward from m to 1 backwardly. And you can, for example, you can choose m to be log kh. And you can bound the original variance, like this term, in the order of O tilde k. Because here you already, expand many times, and then you take the 2 to the negative m. You basically, this term is vanishing as very small. And the only remaining term is the second term, which is k to the 2 to the minus 1. And then but going back, you will have the variance being O tilde k. So the main difference is that many previous work only expand once here. And then if you get some poly h, poly log k terms. So now it's square root of k term, but you still have poly h term in the second term in the regret. But here we need to do many like higher order expansion in order to kill this lower order terms. And I would say that this kind of idea already appeared in some previous work like Timur and Hutter, and recent work by Li et al. This year for some generative model. All right, so these two techniques, one is monotonic value propagation. And so this is the first innovation, and the second one is you do need to use higher order expansion to kill terms, lower order terms that depend polynomially on h. So in conclusion, we present a new algorithm, MVP, which has regret bounds square root of SAK plus S squared A. This is the first polynomial time algorithm with regret scales logarithmically with planning horizon h. And we are only one term away from the lower bound of contextual bandits. Okay. And our automation one extension we did recently is on reward-free reinforcement learning, which also appeared in some previous in one of the previous talk. So together with our technique and some new techniques specific to the reward-free reinforcement learning setting, we can get this kind of sample convex bound. It's S squared A or epsilon squared. And again, it's only log in h, log h in the O tilde. And it basically nearly matches lower bound in the previous work, which proposes this question. Okay. Again, I want to emphasize that the bound does not depend on, polynomially depends on h. So for those who are interested, you can check our paper. And for some open problem, the first most important problem, I think, is to get rid of this S squared A term. If we can get rid of that, we can basically claim that reinforcement learning is just as easy as bandits. I think this is a very surprising and big result. Another open problem is to design a model-free algorithm with regret that scales logarithmically with h. So all existing results either scales exponentially, like running time scale exponentially with this parameter, or like ours, we use model-based approach. So we want to have a model-free algorithm with log h regret. And another direction to generalize this kind of approach to function approximation settings to see whether in, for example, linear MDP, low Bellman rank settings, whether you can get a bound that is logarithmically in h. And I would like to conclude here and take more questions.
All right, thanks very much. That was wonderful, really nice. So there are like a billion questions in the chat. I don't know, there have been like a bunch of different discussions going on. I don't really know where to start. So I actually have a question regarding your proof technique where you talk about this law of total variance.
Yeah.
So actually the first few steps are kind of common, no? So I remember this showing up in the Azar Osband Bonus paper.
It's just you need to expand like many times,
Mm-hmm.
and then you use the assumption that total reward is bounded by 1, or you can bound the variance even in the higher order. So even in the higher order variance is still bounded by, say, HK. And then you just reverse the whole expansion, then you can get Q this term. So I think originally I think previous were mostly just expand once. So even if say here you have an HK bound, but even if you reverse from here, you still have a polynomial dependency on H. But here, if you expand many times, this is basically exponentially a decreasing term. So you can kill this term or by a log HK term. Yeah.
I see. Okay, I finally got it. Yeah. When you first described it, I didn't quite understand like what is this expansion, but you're really just looking at the moments of V star, like all the even moments, and all of those happen to be bounded by the same law of total variance.
Yeah, all the power of moments. Yeah.
That's very nice, very clever. All right. So Chava, do you want to curate the questions? Have you been following the discussion?
I think that most of the questions were resolved. Like András asked the question, and then I started to type answers to that, but then I stopped because I don't actually know what he wants to say. So maybe András, do you want to ask your question?
Okay. Hey. So my question is that if I look at the monotonicity condition in your definition, right, and then you're saying that for any v hat which is larger than v star, so I can set all the v hats to 1, in which case the variance becomes 0, and your f function is just 1 over n. And why is it bigger than the variance of v star?
You need to tune the the variance, like these two constants together.
But I mean, this would say that the variance of v star cannot be bigger than, like, I don't know, 20 over 3 square root whatever, which...
No, I guess what András is asking, like, why does the monotonicity condition hold for the function that you're proposing? Is that?
No, what I'm saying is that if I set v hat to be 1, like constant 1.
Yeah. Does monotonicity even hold?
Then why would the monotonicity hold?
I guess it's a big or something.
Because then f becomes just 1, like 400 over 9, 1 over n. And why would it be bigger than the variance?
Oh, I see. Yeah, so this is the basic idea. So in our paper, there's some it's a little bit hard to expand, but you need to add some additional tricks. But this is the main idea of the this MVP bonus. You can check our paper. So basically, you still need to. So this is a basic idea, but you need to turn it into a kind of summation term so that you can have this monotonicity property. So yeah, a little bit hard to explain here, but you can check our paper.
Okay, maybe I will, because I don't see like how my question was answered, but
it was not. Yeah. It was answered by you check the paper because there are some dirty details that don't fit the slide.
Right. That's yeah.
Or you require actually something more than just that monotonicity. Maybe that's.
It seems that that's the case.
Because just that monotonicity that we had is bigger than v star. That certainly doesn't.
It doesn't hold. That's your example.
I mean, it can hold, but it doesn't imply that
we had to be 1. then there is no variance. Like the variance is
Yeah, you're right. There's some additional dirty details there. Right.
Okay, on about the monotonicity condition.
Yeah, somehow it's
Okay.
probably more complicated or something.
Okay.
It would have been too good to be true to have such a clean proof with these two properties. There are some details as usual.
It's not. I mean, okay, it's not long, but it's not clean as well. I would say.
Yeah. It's basically how you kind of discover that this is going to work, and then.
So this is our motivation. We want to ensure these properties. That's why I said.
Oh, I see.
So, so Simon, when you said that constants matter, like what did you exactly mean? Like, did you mean like these particular numerical constants that you're
usually,
showing?
in constructing bounds, we just set C, this constant to be very large, then you should be good enough. But here, just the scaling, like you need to ensure one constant. For example, here, if I remember correctly, you need to set the second constant is the square of the first constant. You need to have this kind of constant.
Right.
So you need to be more careful about tuning this constant than just setting them to a very large constants.
I see. So if those are not like, one is not the other squared, then you have some trouble in your expansion.
Yeah.
And it seems that people still have some questions regarding this law of total variance. Like Kimon Kuhn is asking that here in this slide 30, in this one, when you like take this 2 to the mth moment of V star, so how heavily does this rely on the fact that the total reward is bounded by 1? So like what if like the total reward would be, I don't know, some other constant, maybe scaling with h?
Yeah, then here you will have that constant, like k square, maybe k times your bound square. And this k.
So I guess like the question is, would that be also raised to this crazy power of 2 to the n?
Yeah. But remember here you also have a 2 to the negative m. So.
Oh yeah, right.
Right. This is dominating.
Yeah, and I guess like one related question would be is that, well, if your rewards with some not to 1 but to some constant b, say, then how would that show up in your final bound? Would it be just linear?
Yeah, so it will be kd here and kd to the power of 2 to the m minus 1 and 2 to the negative m. So you will get the kd here. Sorry, not kd here, but I say kd here. Yeah.
And are these all the terms in your regret bound? Like I'm wondering, if you would have like something like d squared or d to the 3 halves.
You may have some other term, maybe s square ad, I guess.
Yeah, right. Because like assuming that it's 1, it's like sort of hiding this detail, like what is really the scaling with all of this?
Not very clear. Yeah. But nowadays, most people just assume it's like bounded by 1 in some sense.
Yeah, but yeah, and this is really hiding some details. And again, like, I did like a bunch of work on this like combinatorial bandits and shortest paths, and there people really invested some effort in understanding like these scaling factors. And in some settings, I guess in like the full information setting, what has been shown is that the optimal scaling with this kind of scale factor, like the rewards is like square root of the magnitude.